Thank you so much for having me. I will now present okay. Thank you so much for having me. I will now present the result of the work package 5 dedicated to the controlling risk on underground hydrogen storage. It's not working. No. Another mic. Okay.
Maybe you can talk about the picture.
Yes, I can. Like, is it okay? Yes. I'm a police design. I'm from INERIS. INERIS is the French National Institute for Industrial Environment and Risk. I'm in charge of the contribution of INERIS in the HyPSTER project, but I'm not alone here. I come with two of my colleagues, Sylvain Pic, who is a senior safety engineer, and Beno Wimbenger, who is our hydrogen expert in our company. So what can I say in introduction? Okay, thank you. I can talk without a slide if you want. As an introduction, we can say that Europe had made the development of green hydrogen industry as a priority on its strategy to fight or to combat climate change. And the HyPSTER project, perfect. And the HyPSTER project is a great opportunity to develop in France an experimental facilities to store green hydrogen in the salt caverns. What can I say? This opportunity should pave the way for the development of a hydrogen sector at the industrial scale that could be developed across other countries in the world with the technical and economical replicability. From my company, INERIS, as a reference institute on industrial environment and risk, we consider hydrogen as a transitive, energetic, what can I say, promising alternative energy, yes, promising alternative energy to fossil fuel in order to, that can be created with renewable energy or low carbon energy. So INERIS is very proud to contribute in this kind of project. However, we should mention that the safety and the environmental impact of this kind of project remains the major keys on the public acceptance of this kind of project. So INERIS and all the involved partners in this work package has the responsibility to demonstrate that this pilot, this demonstrator can be performed in safe condition with low environmental impact. And that is done with a lot of studies, a lot of analysis conducted together with partners and involved partners in this project in order to demonstrate that all type of risks can be managed in this kind of project. Okay, I have my slide now. So the objective of this work package was first to conduct the pilot experiment under acceptably safe condition, minimizing residual risk and reducing the environmental impact. And the second objective was to identify how safety and environmental lessons from pilots can inform future hydrogen salt caverns in Europe. And the last but not the least, we also have to assess the strength and the weakness of the relevant legislation, the regulation around the standards to provide recommendation of safe development of hydrogen salt cavern in Europe. So what about the challenge? The first challenge was to evaluate the risks, to identify, assess, and control all type of risks that the pilot can pose to people and to environment. We did it. We did a lot of study on risk assessment. We have a risk methodology in my company with the contribution of Storengy and other partners. We also do the geomechanical assessment of the very worst case scenario. As you just saw in the previous presentation, we are trying to do a demonstrator, and for the risk point of view, we try to analyze the very worst case scenario, like if there is a rapid injection of hydrogen, a rapid withdrawal of hydrogen, or if there is a fast cycling of hydrogen. Another good result of this work package is all the work that have been done around the blowout modeling. What is the blowout? The blowout is kind of the very, very worst case scenario we can have here. It's an uncontrolled release of the store project, the hydrogen, when the safety equipment around the well fail. All the store gas or stored hydrogen goes out to the atmosphere, and we did a lot of modeling, the underground modeling and the aerial modeling to calculate the effect distance of this very worst case scenario. Another good result was the authorization. We dealt, mainly Storengy dealt with the administration to obtain an authorization to perform this test in an existing cavern. We obtained this authorization 18 months after the starting of the project. We also have a lot of work on the, in French we call it retour d'expérience, a lesson learned from the project on the industrial safety, and also from the human and organizational factor of hydrogen projects. And we have the chance to publish a lot in this work package with the dissemination of our works. So the challenge was the risk and the environmental impact assessment with INERIS, Storengy, and ESK, the contribution of numerical modeling to cavern storage risk evaluation, as I just explained, the relation with the French administration. We are public, but the relation is with the DREAL, the local administration. And as I just said, the lesson learned on safety and environmental issue and recommendation for future storage. And the last, regulation assessment and recommendation for large-scale deployment in Europe. That was an objective of the project. So I will take the time now to explain a little bit the result of the project. I cannot go deep in all the work we have done in the work package 5, but I will focus on main things. Firstly, on hydrogen. Hydrogen is a special molecule that has characteristics that are favorable to the safety and not favorable to the safety. For characteristics that are favorable to the safety, hydrogen is a non-toxic gas. It's light, so this reduces the risk of accumulation. There is a low radiation flame, so limit risk of propagation. And there's a lot of characteristics that are unfavorable to the safety, like it is easily flammable. As you can see in the graph, the flammability range of the hydrogen is very big. And with that, it has a low minimum initial energy. Hydrogen can generate very violent explosion, can easily leak because of the small of the slit. It can weaken materials. Grégoire talk about it. We can implement it at very high pressure. It is difficult to detect as invisible, odorless, etc. But all these risks can be controlled. At INERIS, we have decades of experiences manipulating in the hydrogen in industrial environment. We regroup all the risks in 4 main categories. The work package 5 really focuses on geological and safety risk, while, as you just saw, the technical and economic risk was dealt in the work package 3, work package 4, and the operational risk, like hydrogen embrittlement, the choosing of material was done in work package 3. So for the safety risk, as I just said, we have the high flammability, the explosion hazard, we studied it in this work package. Flash fire, jet fire, explosion, anoxia risk. And what about the geological risk? About the cavern stability, we want to store hydrogen in a soil cavern. We want to inject and withdraw very fast hydrogen. What about the mechanical stability of all that? What about the tightness of the well bore, the soil creep, the presence of soil, of fault or fracture, etc. We study all this in this work package. Okay, a few words on risk analysis. We conducted together with Storenzi risk analysis on this project, and the risk analysis was started with the preliminary risk assessment, and that was done in the 2 platforms. The first platform which is the platform for the hydrogen storage in cell cavern, and the second platform, which is the platform on the hydrogen production. There was a clear methodology. The study was led by my colleague Sylvain Pic, that study the product hazard in the system, the brine, the hydrogen, the compressed air, the nitrogen, etc. The process and the equipment hazard, we review all the equipment involved in this test in those 2 platforms, together with surface facilities, etc. We try to learn from the existing documentation on what how company deal with hydrogen in soil cavern, what type of accident they have, etc. And we conclude with a result that define kind of major hazardous phenomena. That was flash fire, jet fire, explosion, burst, or toxic effect. And the central fear event was mainly the loss of hydrogen containment, the ATEX formation, the overpressure, and release. Okay. For the geological risk, we decide at the very beginning of the project not to study only the EZ53 soil caverns. Why? Because the cavern is very experimental. It's very small cavern. Only 82 tons of hydrogen can be stored in that cavern. And if we withdraw the consent volume, only 40 to 42 tons can be used. And that's why we choose to study also a kind of a generic cavern with a bigger size, 500,000 cubic meter in geometric volume, comparable to one cavern that is used now in the United States to store hydrogen in Clemens Dome. So we did a lot of study because we wanted clearly to know in the study of the very worst case scenario, as I just said, rapid depressurization, fast injection, fast cycling. We wanted to know what is the behavior of hydrogen inside the cavern, and how can cycling or loading, displacement of this hydrogen inside the cavern can affect the mechanical stability of the cavern around the soil cavern, the rock mass around the soil cavern. So we divided the problem in 2. In the modeling, there's a problem, the wellbore problem and the cavern problem. For the wellbore problem, you need a wellbore hydrogen pressure and temperature, massive flow rate, hydrogen properties, temperature and pressure, velocity, etc. And for the cavern problem, we did kind of a couple modeling from thermodynamic to the geomechanic to really assess the strength, the stress, the creep closure, the subsidence, and etc. And to assess the mechanical stability, we use some criteria. First, for the thermodynamic modeling, we develop a model that states in its equilibrium equation that the internal energy inside the salt cavern should be in equilibrium with the head flux coming from the rock mass plus the enthalpy of the injected hydrogen and the possible condensation of hydrogen inside the salt cavern. This model was already validated in natural gas cavern, and we are willing to finish the cyclic test to revalidate it with real EZ53 data. So as I've just said, we use some mechanical criteria to evaluate the stability of the salt cavern. The first one was the creep closure. The rock salt has a very complex behavior. It's elastoviscoplastic, it's highly sensitive to temperature. When we model this, the behavior of rock salt and the behavior of the cavern, we use creep law. We use in this project, we use a very complete creep law that takes into account the dislocation creep, the primary and the secondary creep, and also the pressure solution creep. That's important when the salt is under very low deviatoric stress. So we don't want to have traction at cavern one or in the rock salt. It is another criteria. So when we're doing numerical computation, the least compressive principal stress should not be a tensile stress. And we also have a criterion around the dilatancy. The dilatancy is kind of it's kind of, okay, 5 minutes, which kind of the criterion where when the deviatory stress has to be very higher comparing to the mean stress. So we did all this modeling in a software developed by a HyPSTER partner, Benoit Brois, called Locus 3D. And I can show you some result here. Here I'm showing the result of the deviatory stress and the factor of safety of the salt caverns when the salt cavern is submitted to a blowout. When there's a blowout, the pressure drops to the atmospheric pressure. And as you can see in this modelization result, there is evolution of the deviatory stress around the salt cavern, and there is a zone around the salt cavern, a very close zone where the salt is damaged. And I also show you the result in terms of displacement. We also calculate the vertical displacement and the horizontal displacement around the salt caverns. I should say that for this modelization, it's a very, very worst case scenario. So the cavern is fully full with hydrogen, which is not the case in the HyPSTER project. As Gregoire just saw, we will fill only the upper part of the salt cavern. You can see the evolution of vertical displacement around the cavern. Okay, after this result, we did a lot of numerical computation when the hydrogen goes out following, for example, the failure of wellhead. We can modelize the dispersion of the hydrogen in the atmosphere, as you can see in 2D and in 3D. And we can compare, we did a lot of comparison with methane to see how big is the extension of the cloud when the hydrogen goes out in the atmosphere. And to represent this distance, I put a salt cavern in this room, and you can see the distance from here. The red point is here, and the red point is here, and the green point is the Austerlitz station. You can see that with a blowout, an explosion with hydrogen can have a 600 meter of effect distance. Few words to finish on human organizational factor. We In this project, we work on the return of experiences on human and organizational factor. As we know that safety is not only technical, there's people behind this, all this, and there's a lot of study thanks to the HyPSTER management projects that allow engineers to perform this kind of study. We intend to pursue until the end of the project. And my last slide will be regarding the regulation. We did a lot of work on the normative to follow the normative and the regulatory framework related to the hydrogen storage in salt cavern in France and Europe. My colleague Beno Wemberger is in the room. He presented this result in Canada last year at the UHS this year. And he'll be pleased to answer all your questions. So what's the next step of this kind of work? First, we want to pursue the modelization of worst case scenario. We want to improve the model, the thermodynamic model of salt cavern with the in-situ measurement that will come in 3 months from Storing. We will try to model the hydrogen leak path to cement, rock salt, porous media. As you clearly know, we know how to evaluate the damage zone around the salt cavern. We want to go deep on that. We want to pursue the 3D model and the geomechanics to assess if there is a neighbor cavern or not. And we should pursue the lesson learned on safety. There's still work to do on this. And we are following at INERIS the regulatory framework, and we are providing recommendation at the good level to the safe deployment of the underground hydrogen storage in France and in Europe. Thank you so much for your attention.
Thank you. Thank you. Do we have some questions? Perfectly clear. Oh.
I have many questions. I'm Sylvie from Equinor, but maybe just your thoughts on, public acceptance of having several tons of hydrogen stored subsurface close to where you live, or in this not in my backyard type of policy. So in terms of having, for the HyPSTER cavern, you have 3 tons of hydrogen stored there, or you will have in a short while. And given the fact that the downhole safety valve, as I understand, was not properly tested, it will be tested by the end of the project. So how do you do like workover operations on the wellhead when the downhole safety valve is not properly tested with people around on top of that? Do you have any thoughts on that? So regarding safety distances, snubbing operations, things like that?
I will start the answer, and I will give the floor to my colleague Beno to complete, and maybe Stoanji will have a few words on that. We have the chance with the HyPSTER project that we are already in an industrial site. It's an existing cavern in industrial site with a lot of cavern around. I will give the floor to my colleague Beno to complete.
Yeah, but can I also just ask another question? What are the risks of having oxygen into a cavern when you have these cycling operations? Are there any risks at all connected to that?
Well, I might answer to this question of oxygen. Well, oxygen, the lower content of oxygen is 5%. When you get about 5%, you can get an environmental mixture. So for sure, you have to manage this absolutely, and as well as you are involved in the production of hydrogen with electrolyzer, you have to manage the existence of oxygen what could appear. So you have to control that the level of stays always lower than 5%. For sure, that's the safety basis. Coming back to your question regarding the acceptance, social acceptance, right? Was this somehow the scope? Well, we are not very well aware about to handle this in the when, but we are very well about the regulatory scope that exists today. So in France, we have a threshold of 1 ton stored hydrogen today. So you have to make your danger study, which is somehow giving you the trust about to handle the hydrogen on site of your site. Yeah. I'm not sure if this is concretely going to the question you had. Is this, yeah. Yeah. Well, hydrogen is very well known. Yeah, we have in France about 1 million tons of hydrogen, which are used each year. In Germany, it's about 2 million tons, and there are very few accidents. So the first thing what you have to do is that you have to put in place some protocols for handle it. And this has been done as far as I know. And if everybody around the site knows what are the risks which are related to it, and that they take care about these protocols, you can handle it without any accidents. So it's only a question of formation. You need to form the persons which are on site. That's the main point. But like we have seen before, hydrogen has very specific characteristics, very different to natural gas. And this has to be known. If you look to the lessons learned about hydrogen in the past 20 years, the most accidents that happened because the people involved in hydrogen, they haven't been formed enough. That's the problem.
We have a question online. Olivier is asking, what standards are you recommending for hydrogen pressure vessels like valves?
It is a question for Storenji. But there is no Grégoire. Okay.
Maybe we can send the question to Grégoire and he will give an answer.
But I want to say some few things about the annular safety valve. You can't say that the valve was not tested because it was specific done by Schlumberger. Schlumberger designed annular safety valve, test it before providing it to the project. You understand?
Yeah.
But
no.
Okay.
Tested after it's installed, right?
It's been tested to nitrogen.
Yeah, but
Not to hydrogen, but in most wells, you don't necessarily test it to the final fluid that's in the natural gas. When you install the compression, you test it to nitrogen, for example. Then you move back to brine, and then you displace to natural gas. Not necessarily tested to the final fluid in the storage.
Okay. So saying that there are many ways to test, and I'm pretty confident that this valve was tested before providing to the project.
No, just to summarize what I said, I was mentioning that it's not necessary on all the wells. We don't necessarily test the final completion equipment which is installed in the well to the final fluids which will be stored. It can be tested to nitrogen, to the required pressure, and it's deemed as a integrity barrier, you know. And then the storage is moved to natural gas or hydrogen. It's accepted. Maybe not in Norway. But
Okay, thank you. Thank you, Hippolyte.